Hello everyone, welcome back to BC Calculus. Today we're in lesson number 41 where we're going to start talking about sequences and series. In lesson 41 we are focusing just on sequences. For majority of BC Calculus we are going to focus on series more than sequences. So this is just one quick lesson just to refresh your memory on what you guys did with sequences back in pre-calc honors. So one thing that we want to say about a sequence is it's just an order of numbers. So we're just going to be listing numbers, first term, second term, third term, etc., etc., etc. We can list a sequence based on whether it's explicitly written or recursively written. Explicitly written would be something like 5, 10, 15, 20, 25. So we're adding 5 to each term. Recursively would be dependent on the previous term. So it could be an expression that a to the n is equal to n2 to the n minus 1 plus 5. So we would have to take the previous term and then do 2 raised to that power plus 5. And so that would be what the recursive one would look like. So let's go ahead and talk about how to represent these sequences. And the first thing is giving you the function that 1 minus 1 over n, where n is greater than or equal to 1. So if we want to find this sequence, we just start listing things out. Well, when n equals 1, that's where we're starting. We plug in 1 here. We get 1 minus 1 over 1, which is going to give us 0. We plug in 2, we're going to get 1 minus 1 half. Well, 1 minus 1 half is going to equal to 1 half, right? If I plug in 3, I get 1 minus 1 third, which is going to give us 2 thirds. And then we can just keep going, 1 minus 1 fourth is going to give us 3 fourths, etc., 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 etc. And then let's go one more. So 1 minus 1 fifth gives us 4 fifths. So you guys can see that this is a sequence by listing numbers out like so. So this would be a sequence of our numbers based on this formula that we have right here, where n is greater than or equal to 1. And we could do that for the rest of these problems. Another way that you guys could have seen this is you could have actually rewritten this problem before you did it by combining fractions and just get n minus 1 over n, right? So these are equal to each other. So that's probably an easier way to actually look at these problems. And so now we can see that, the numerator is always 1 less than your denominator. So that's just a way of writing something, and this is, again, an explicitly written sequence. So if I look at example number 2, then, again, I just start plugging in numbers. Well, this says that n is equal to 1, so this is where we're starting, so this is another way of looking at it, and then we're going to go up to positive infinity with it, which we'll get to in a minute. So if I start looking at n equals 1, then, again, we plug in, and we're going to get 1 over 1 is 1, and if this is going to be 1, it's negative 1, so it's going to end up being 0. If I plug in 2, I'm going to get 1 half. Well, this is actually going to make it a positive 1, so it's going to be 1 plus 1 half, which is going to give us 3 halves. And then if I equals 3, again, this is going to be negative. So notice that for all the odds, this is going to be a negative value, so I'm subtracting, and then for all the evens, I'm going to be adding. So this is going to be 1 minus 1 third. So this is going to give us a 2 thirds. And then a of 4 is going to be 1 plus 1 fourth, which is going to give us 5 fourths. And then a to the 5th will be our 5th term. Again, we're going to subtract 1 minus 1 fifth, which is going to give us 4 fifths. And so we can kind of start seeing what's going on with this problem. And then, again, we write this sequence out as 0, 3 over 2. And again, this has to be implicitly written. We will do some recursive ones in a little bit of time, like so. And we can continue on with it as well. And our general formula would be actually what you see right here in this bracket. And then the last one is just talking about what is already given us our terms. So in the first one, we're giving you a formula, and we're saying, okay, we want n is greater than or equal to 1. And the second one, we're given the formula, and then we're just looking at brackets. Well, this is where n starts, this is our infinity, and this is telling us what this is. So this is c of 1. This is going to be c of 2. This is going to be c of 3. This is going to be c of 4. So we've already listed them out for us, as we can see, and this is going to be our formula. This will be actually what our c of n is actually equal to. So one thing that we want to talk about now is whether a sequence converges or not. So in order for you to understand if a sequence converges, it's one very simple process. Does the limit as n approaches infinity of the function, does it actually exist? If it exists, then it will converge. If it doesn't exist, then it will diverge. So let's look at these 3 examples again, and this is what this part right here says. consider the three examples above, which one's converges and which one diverges. So there's a couple ways we can look at these problems, guys. The first one is, well, let's look at example number 1 again. Well, I already told you guys that number 1, we can rewrite it as this. Remember, it's the limit as n approaches infinity of a sub n. Well, a sub n can be rewritten as n minus 1 over n. You guys already know that this limit does exist, right? Because it's a rational function. The highest degree in the numerator is equal to the highest degree in the denominator. They're both equal to 1, so their limit is going to be actually equal to the ratio of their coefficients, which ends up being 1. Well, and that's exactly what's happening here. If we start looking on our graph and we start at 0, and then we're looking at 1/2, and then we're at 2/3, and then 3/4, and then 4/5, we are approaching y equals 1, right? This is getting a little bit bigger. Think about it like this. This is 0, this is 0.5, this is 0.67, this is 0.75, this is 0.8. We are getting closer and closer and closer to 1. So that's one way to look at the problem. You can actually start graphing the problems too if you want to, because this may be a little bit more challenging for you to see whether or not number 2 actually converges or not. But we can look at it 2 different ways. The first way is splitting the limit up. So let's find the limit as n approaches infinity of our function 1, and then we can also add the limit as n approaches infinity of -1 to the n all over n. And so we can look at it like this. Well, the limit as n approaches infinity of any constant is simply just going to be that constant. And then if we look at the second one, so plus, so what's going on right here is we're looking at our problem, we have some number at the very top, and this is really important to understand, that no matter what n is, it's going to be a positive or -1. It's to be some number, and it's all over a n. So some number over n. This is a bottom-heavy function. So if we look at this actual example, we're going to get that this is going to end up being 0. This limit will approach 0. It will approach it bottom, top, as it eventually gets to that thing. So we're going to go looking something like this, but it's going to eventually get to 0. So this overall limit is actually 1. Another way of looking at this, guys, is if you actually were to sketch these numbers, you can see that we're starting at 0, and then that we're at 3/2, then we're at 2/3, then we're at 5/4, then we're at 4/5. And so you guys can see that as we're getting closer, we're actually starting to get closer into 1. We're starting to look at 1. And then the last example here is, let's see what's going on with this. Well, example number 3. Well, this limit, we're oscillating. We're oscillating here. So it's -1 infinity plus 1 over n. So if we look at this breakdown of this one, we look at the limit and we split it apart, this limit's actually not going to exist, this little piece right here, because when n is positive, even, then this is going to be a positive 1 limit. If n is negative, it's going to be -1. So it oscillates between 1 and -1. So this limit doesn't exist. For this sequence actually is a divergent sequence. So it actually diverges. That's supposed to be a G. So a divergent sequence. For 1 and 2, well, you guessed it, because the limits that exist, it doesn't matter what the limits is, they are convergent sequences. So I just want to say again that this is only for a sequence that a limit has to exist. If for a series, whole different ballgame. So let's actually go over to a couple of examples to see what we can do with this. So these questions are actually asking us to determine if the sequence converges or diverges, and if it converges, then find this limit. So we're talking about, again, if this sequence converges. So basically, again, does the limit as n approaches infinity of a of n actually equal some value? Well, guys, just like I said before, this highest degree in your numerator is equal to the highest degree in your denominator, which means that we have a limit. We have a limit of the ratio of our coefficients, which is going to be 1/2. So therefore, this is going to converge. And the fact that the limit's actually going to be equal to 1. So if we were to start plugging in values of n, it would eventually get to the point that it goes to 1/2. And you guys know this by horizontal asymptotes. If we look at the next one, the limit as n approaches infinity, again, of this rational function. You can see that the highest degree in the numerator is equal to the highest degree in the denominator. So this is getting a little boring with this one. This is also going to be converging. And then for example number 8, you guys can see that the limit as n approaches infinity of a of n is equal to, well, now we're bottom heavy. We're bottom heavy. So we're just looking at the least coefficient. This is 1 and this is 2. Well, since we're bottom heavy, this always is going to be 0. So again, we have a convergent series. If it had been top heavy, then the answer would be it diverges, because our limit would be going to positive or negative infinity. When our limit does go to positive or negative infinity, then it's going to definitely diverge. We're looking for a value here, a value L, not some positive or negative infinity. So for example, number 9, you guys can look at, again, that this limit of this limit, as n approaches infinity of our ace of n, this little piece right here, so just n over n plus 1 is actually going to give us 1. However, just like the conversation we just had, if I were to look back and forth, whether it's odd or even, then it's going to give us a positive or a negative number. So again, this is going to oscillate, so therefore this is going to diverge. This is going to diverge. This is going to oscillate between 1 and negative 1, so this limit will not be existent. For example, number 10, I want you guys to just, and again, we've actually already had this conversation in this video, that if you look at this function, this is n, obviously, in the bottom, but this will always be a number. It will always be a number. So if this is always a value, because no matter what I put in there for n, I'm going to get a number all over n here. So this number over n is a bottom-heavy function, so it's going to converge. It's going to converge and actually converge at 0. One thing that you guys can absolutely do if you want to is start plugging in numbers and kind of seeing what's going on with this. Yeah, if you look at ace of 1, it actually ends up being 1. Ace of 2 ends up being 0. Ace of 3 equals negative 1/3. Ace of 4 is equal to 0. And ace of 5 is going to be equal to positive 1/5. If you keep going with these problems, you're going to see that it's going 1, 1, 1, 1, 1. And then it's going to keep going back and forth to, negative 1/7, and then positive 1/9, negative 1/11, positive 1/13. These numbers are getting really, really, really small. So it is oscillating around 0. And every even one's actually at 0. So it's going to look something like this. But it's going to get closer and closer and closer, even though we're on there. And that's a really bad picture. But just understand that if we have a number over n, then it's going to always be 0 because it's bottom heavy. So speaking of bottom heavy functions or actual function dominance, if you look at example number 11, we look at, e to the n over n squared. Well, one of the things that we can do for this one to see what's going on is when n is equal to 1, we get e and we get 1. Well, e is bigger than 1. When n is equal to 2, we're going to get e squared, right? Remember? And this is going to be 4. Well, e squared is much bigger than 4. And then if we go to 3, we're going to get e cubed, and then we're going to get 9. And e cubed, obviously, because e is 2.7. So 2.7 quantities cubed is going to give us a much bigger number than simply old 9 is. So we can see that this is a functional dominant problem here in the numerator. Well, in this case here, this is going to actually not exist because we're functionally dominant in the numerator. Therefore, this is going to diverge. Now, another way you guys could have done this problem, if you didn't like it, could apply L'Hopital to this. So L'Hopital is actually alive and well with these problems. So if L'Hopital doesn't work, then you would get, because you would put in this, you get infinity over infinity. So then I could do L'Hopital with the problem, and I get e to the n times all over 2n, which would give you infinity over infinity. And then you would do the limit as n approaches infinity of e to the n over 2. Again, we have a higher number. This is going to be approaching infinity. This is always going to be approaching 2. So in this case right here, we know that this limit would actually be infinity. So again, it would diverge. It would diverge. So that is what we're going to do for this problem set. I'm going to stop here, and then I'm going to continue on with the rest of the problems in the next video. So I will see you guys in the next video. I'm sorry that was very rushed.